In this deck, we focus on a coordination problem that appears whenever a port complex runs multiple specialized terminals. Inter-terminal transfer. A container can arrive in one terminal for discharge, but need to move to another terminal for transshipment, a different service, or different vessel connection. The operational objective is to move containers between terminals efficiently while managing fleet capacity, routing, congestion, and timing. If transfers are slow or poorly coordinated, downstream vessel loading is delayed, yard space is stressed, and the port loses throughput and reliability. Many large ports operate as terminal networks rather than a single site. In the Port of Los Angeles, a container unloaded at one terminal may need to be transferred to another terminal to connect to a departing vessel. In the Port of Rotterdam, containers can be redistributed between terminals as vessel schedules and capacity constraints change. As port operations scale to millions of 20-foot equivalent units per year, this becomes a system-level optimization problem. You must coordinate vehicle fleets, routing paths, congestion, and terminal operating windows while controlling cost and environmental impact. Interterminal coordination matters because it connects the port into one functioning network. A great plan inside one terminal can still fail if the transfer network cannot deliver containers on time to the correct destination terminal. Strategically, good interterminal transfer decisions reduce vessel waiting, improve port throughput, and increase supply chain reliability. Poor decisions create hidden delays that surface as missed cutoffs, queuing, and lost competitiveness. We solve the interterminal transfer problem through a tiered toolkit. Tier 1 provides a mixed integer programming model that captures assignment, routing, and timing decisions with explicit constraints. Tier 2 uses a priority-based assignment heuristic for fast, deployable decisions. Tier 3 applies a genetic algorithm to explore better assignment and routing combinations. Tier 4 uses reinforcement learning to learn sequential assignment policies. Tier 5 embeds decisions in a digital twin for what-if analysis and investment evaluation. Tier 6 explores a distributed multi-agent ecosystem with auctions, negotiation, and incentives. Tier 1 models the transfer system as a constrained optimization problem. You decide which vehicle handles each container, which terminal-to-terminal movements vehicles perform, and when those movements occur. The formulation is valuable because it makes all coupling explicit. Vehicle capacity, container readiness times, movement costs, and flow consistency across terminals. This slide defines the core sets: containers, terminals, vehicles, and time periods. Operationally, these sets define the scope of decision-making. The model is not only assigning containers to vehicles, it is scheduling how the fleet moves through the terminal network over time. Parameters include distances between terminals, per-distance operating costs for each vehicle, and vehicle capacity. You also have service time at each terminal, plus container-level fields such as origin terminal, destination terminal, ready time, and a weight or size factor. Operationally, ready time is critical. Assigning a container before it is ready produces infeasible plans. Weight factors matter because vehicles have limited capacity and not all containers consume equal capacity. Decision variables include whether a container is assigned to a vehicle in a time period, whether a vehicle travels from one terminal to another in a time period, and whether a vehicle is deployed in a time period. Operationally, these variables allow the model to trade off fixed vehicle deployment costs against travel costs and service performance. The objective combines two cost components. First is variable travel cost, vehicle operating cost per distance multiplied by the distance traveled. Second is a fixed cost for deploying a vehicle in a time period. Operationally, this prevents a trivial solution where you deploy every vehicle all the time. The model must decide when deploying another vehicle is worth the cost. The assignment constraint ensures every container is assigned exactly once. Operationally, this prevents two failure modes: dropping containers to reduce cost or duplicating service in a way that looks feasible numerically but is not physically meaningful. The capacity constraint ensures the total weight of containers assigned to a vehicle in a period does not exceed that vehicle's capacity. Operationally, this is the core feasibility rule. Without it, the optimizer could overload a vehicle to reduce travel cost. Flow conservation ensures vehicle movements are consistent across terminals. If a vehicle leaves a terminal, it must arrive somewhere, and its location must evolve consistently. Operationally, this prevents teleportation. A vehicle cannot appear at Terminal C without traveling from another terminal. Timing constraints ensure that assignment respects container readiness. A container cannot be scheduled before its ready time. Operationally, ready time is a hard constraint in real ports. A container may not be released from a vessel, a yard block, or customs until a specific time. Deployment constraints link vehicle travel decisions to whether the vehicle is considered in use in that time period. Operationally, this is how the model activates fixed cost only when the vehicle is actually deployed. This slide visualizes the inter-terminal network. Use the diagram to build intuition. Terminals are nodes, travel legs are edges, and the optimization chooses which vehicles traverse which edges to move the correct containers on time. This example uses 3 terminals and 5 containers transferred using 2 vehicles. Each container has an origin, destination, ready time, and wait. Distances between terminals are 3, 5, and 4 kilometers. Vehicle capacities are 3 containers for Vehicle 1 and 2 containers for Vehicle 2. Operating costs are 10 per kilometer for Vehicle 1 and 12 per kilometer for Vehicle 2. The reported optimal solution assigns containers 1 and 4 to Vehicle 1 and containers 2, 3, and 5 to Vehicle 2. The reported total cost is 168 monetary units, and the reported completion time is 3 periods. The point is not only the number, it is that the model simultaneously respects readiness, capacities, and travel costs. Tier 2 provides a practical heuristic for daily operation. It builds a solution iteratively by selecting the next container from a priority queue and assigning it to the most cost-effective feasible vehicle. The priority queue combines urgency, such as earliest ready time, with assignment cost. Operationally, this creates fast decisions that usually produce a near-optimal plan. This slide reports a time complexity of roughly quadratic in the number of containers with an additional factor for the number of vehicles. Operationally, the reason is the repeated evaluation of feasible vehicle assignments. The benefit is speed compared to exact optimization. This diagram visualizes the heuristic loop. Rank containers, evaluate vehicles, assign, update capacities and availability, and repeat. Operationally, the update step matters. Every assignment changes remaining capacity and changes what is feasible next. In the first code section, you typically see how containers are represented and how the priority score is computed from ready time and cost. Operationally, make sure the priority definition matches the terminal's service objectives. If you overweight cost, urgent transfers may miss deadlines. This section usually selects the best vehicle for the current high-priority container, subject to capacity and readiness constraints. Operationally, this is where feasibility checks prevent overload and premature scheduling. This section typically commits the assignment, updates remaining capacity, and produces a partial route plan. Operationally, the value is that the algorithm stays simple and fast enough to run repeatedly as conditions change. This slide reports the heuristic output on the 5-container 2-vehicle example. It assigns Vehicle 1 to containers 4 and 1 and Vehicle 2 to containers 2 and 3, leaving container 5 unassigned. The reported total cost is 182 monetary units. The operational message is that heuristics can be close, but small feasibility details like ready times and limited periods can cause residual unassigned work. This slide states the heuristic is within 8% of the optimal solution. Operationally, this is the core trade-off. A simple method provides speed and usability at the cost of some suboptimality. Tier 3 uses a genetic algorithm to search a broader space of assignments and routing sequences. Each individual encodes which vehicle handles each container and in what sequence. Fitness is defined as negative total cost, with infeasible solutions penalized. The goal is to improve beyond the greedy heuristic by exploring global structure. This slide shows the evolution loop: selection, crossover, mutation, and repeat. Operationally, you should interpret crossover as recombining good partial routing patterns, and mutation as injecting diversity so the search does not get stuck. This section typically defines chromosome encoding and population initialization. Operationally, encoding must preserve feasibility as much as possible. Otherwise, the algorithm wastes time generating invalid candidates. This section often defines the fitness function and penalty design. Operationally, penalty calibration is critical. Penalties must be strong enough to enforce capacity and timing rules. This section usually implements selection. Operationally, selection controls exploitation. It increases the probability that better solutions produce offspring. This section often implements crossover. Operationally, crossover must maintain meaningful routing fragments. Otherwise, it breaks good patterns and slows convergence. This section typically implements mutation. Operationally, mutation helps escape premature convergence by introducing controlled random changes in assignments and sequences. This final section typically runs the main evolution loop and logs best fitness over generations. Operationally, convergence logging is how you confirm the algorithm is steadily finding better routes. This slide reports best cost improving from 195 to 175 to 168 to 165. The reported final solution uses 2 vehicles with total cost 165 monetary units. The key message is that metaheuristics can improve solution quality beyond simple rules. This slide reports a 2% improvement over the heuristic. Operationally, the improvement comes from discovering more sophisticated container-to-vehicle assignments and better routing sequences. Tier 4 models interterminal transfer as a sequential decision process. The agent observes the system state, assigns the next feasible container to a vehicle, and receives reward feedback. This is useful when demand patterns and congestion conditions change. Learning-based methods can adapt online rather than relying on a fixed priority rule. This slide defines the reinforcement learning framing. The state includes container status and locations, vehicle positions and capacity, and time context. Actions choose a container and a vehicle. Reward balances cost, delay, and utilization, so the policy learns to make assignments that are cheap, fast, and operationally efficient. This diagram shows the agent environment loop. Operationally, think of it as repeated learning from dispatch outcomes. The agent improves by seeing which assignments reduce cost and prevent congestion. In the first code section, you typically define the environment, initialize the network, and set exploration behavior. Operationally, exploration is needed for learning, but should be controlled. In real deployment, exploration is limited and learning is mainly done in simulation. This section usually selects actions, executes them, and stores transitions. Operationally, storing experience is what allows the agent to learn from both good and bad assignments. This section typically samples mini-batches and updates the network. Operationally, stable learning is required so the policy becomes consistent and reliable. This section often updates a target network and manages exploration decay. Operationally, these safeguards reduce oscillation in learning. This section usually computes rewards and episode metrics. Operationally, metrics help confirm that cost drops and utilization improves over training. This section typically evaluates the policy periodically against baselines. Operationally, evaluation tells you whether the learned policy is truly better than heuristics and metaheuristics. This final section typically finalizes training and outputs the learned policy. Operationally, deployment requires monitoring and fallback rules for unexpected conditions. This slide reports training over 1,000 episodes. Average score improves from -45.23 at episode 0 to positive values by later training. By episode 500, average score is reported as 28.73, with epsilon near 0.010. The key message is that learning improves steadily as exploration decreases. This slide reports the final policy assigns Container 1 and Container 4 to Vehicle 1 and achieves total cost 158 monetary units. This is described as a 4% improvement over the genetic algorithm. Operationally, the policy is learning not just cost but also future implications of assignments. Tier 5 introduces a system of systems digital twin that synchronizes terminals, vehicles, traffic, and external conditions. The twin uses real-time data streams to keep a virtual replica updated and supports what-if decision support. This is how ports evaluate investment decisions and emergency response plans before acting. This slide presents the architecture for real-time synchronization between physical operations and the digital twin. Operationally, the architecture ensures data and decisions flow both ways. Sensing updates the twin, and recommendations flow back to dispatch and routing control. This slide reports example update frequencies, container position updates every 30 seconds, and vehicle status updates every 10 seconds. Congestion, weather, and vessel schedule signals feed prediction and optimization loops. Operationally, these streams allow the system to respond before congestion becomes severe.